Hi, welcome to another episode of Ordinary Differential Equations. Today we are going to talk about examples of second order equations. We are going to concentrate on the simplest type, and the simplest type we refer to them as homogeneous constant coefficients. So if you remember from the last lecture, homogeneous simply means right hand side is zero. Physically that meant external force doesn't exist, and we just have the spring force and the drag force. Constant coefficient refers to the ideal situation where these three entries are just constant numbers. Now I've gone ahead and listed the 7 possible cases that you're going to see. Sometimes the students make a mistake when some of the entries are zero, so I have taken the time to make a list of all possibilities so that confusion goes away. So let's just start. Our simplest example last time was this equation, y double prime plus 5y prime plus 6y is equal to 0. Remember, this was the characteristic equation. The roots are obtained very easily, and the solution is exponential of either of these two characteristic roots times some as yet unspecified constants. Now, what if this term is not there? This represents the spring. What if it's not there? Well, your equation becomes like this, and I hope everybody sees that the roots are 0 and minus 5. And when you write that same expression here, one of the terms becomes exponential of 0t. So of course exponential of 0 is 1. You have to simplify this thing to just a constant, and the other one stays. This is correct, but it's bad form to leave it like that and not to simplify it. So I recommend you do the simplification. Here's another case. What if the middle term becomes 0? In this case, our equation becomes like r squared minus 9 equal to 0. We have two roots that are negative of each other, and the solution becomes some multiple of exponential of one number times t and the negative of that number times t. There are other ways of writing this using so-called hyperbolic trig functions, but let's keep it in that style. Then we went to another type of category where the solution became complex. For example, we saw this equation last time. This is the characteristic equation. The roots are so-called complex conjugates. They're a pair of complex conjugate answers. We said the solution, instead of being written in that style, we are going to be writing it with real appearance, which means we are going to use sine and cosine function. The solution becomes exponential of minus 3t times a cosine of 2t and b sine of 2t. So here's the real part becomes the exponent. The imaginary part here, just the 2 itself, becomes the so-called frequency. This we are going to see later on. This is a situation where the spring has more of an influence than the drag, and we do actually see the oscillations. Next up is, what if that drag force goes away and we just have a so-called pure oscillations? It becomes like y double prime plus 4y equal to 0. Characteristic root equation becomes r squared plus 4 equal to 0. When you write the solution of that, the real part is 0 and the answer is just pure imaginary, which you write it as just plus or minus 2i. In this case, the exponential portion will have 0 in the exponent, so that has to be simplified again, and the solution becomes this pure oscillatory function. Then we went to the threshold situation between the case where we have two distinct real roots and two complex conjugate roots. There is an intermediate case. If you remember, the discriminant became 0, like the following example. If I have this equation, the characteristic equation becomes r squared plus 6r plus 9 equal to 0, which if you factor is just r plus 3 squared equal to 0. The roots become identical. And in that case, that causes another style of solution to emerge. It becomes exponential of either one of these numbers times a polynomial. It's just a linear polynomial here. Finally, the most extreme case, we have no drag and no spring, just y double prime equal to 0. The characteristic equation simply r squared equal to 0 and the roots are 0, 0. If you write the solution in that case, it becomes exponential of 0t times at plus b. And again, this better be simplified. If you leave it like that, it's not a good presentation. You simplify and the answer is at plus b. Okay, these were the 7 possible cases of homogeneous constant coefficient cases. We went through all of them. All the numbers were chosen in these examples to be kind of nice and friendly numbers, so though we don't get tied down with all sort of arithmetic. Let's go look at a problem that is a little bit more mature. Here's an example. Find the threshold time tau. Sometimes they call it critical time. This is the Greek letter tau, after which the magnitude of the solution of the following homogeneous constant coefficient case with this initial condition is less than 0.01. Here's another way of stating the same requirement. That is, find the time tau such that y of t is less than 0.01 in absolute value for all time t larger than tau. Okay, so this is a very standard problem. We want to go solve it mathematically, see how we use a software or estimation to solve it. And later on, we are going to come back and talk about what does this mean. So if you remember, this represents some sort of oscillation. Mass is 1. Drag coefficient is 1. The spring constant is 10. The spring constant kind of dominates. We are going to have lots of oscillation. We have initial position and initial velocity. So we are going to see as a result in example similar to the following case. It will be something like this. We are going to use initial condition to figure out what A and B are going to be. And in that case, we are going to get a bit of numbers not so rosy as just 2 and 3s, but a little bit more mature and perhaps not so friendly numbers. The question is, such oscillations are going to die out because of the presence of the friction. If they die out, then their magnitude is going to decrease. And a standard engineering question is, at what time are you going to call it quits and say, well, this magnitude has died down enough, let's go to plan B or whatever. So there is always some sort of threshold time or critical time after which you are going to declare the oscillation as dead. So we are going to find the solution, we are going to find what the A and B are going to be, and then we are going to talk about how is this going to decline in time, and at what time does it become smaller than a certain amount. So let's go ahead and set out and do that. Again, by now, I'm sure everybody expects this thing, that I'm going to delegate this thing to you. Go ahead, probably spend something like 3 or 4 minutes to actually get the solution. So get the solution, find out the constants, and then the next phase is, well, what do we do next? How do we figure out when is this oscillation have become weakened enough? Okay, go ahead and do that, and then restart this video. Okay, so what do we do first? We, of course, write our characteristic equation. R squared plus R plus 10 is equal to 0. So this is not easily factorable, so we have to bring the big guns, which is the quadratic formula, minus the middle term, plus or minus the middle term squared, minus 4 times the first and last coefficients divided by 2. So minus 1 plus or minus square root of this minus 39 over 2. So the number doesn't come out of a radical. We just leave it like that and write this thing as minus 1 over 2 plus or minus. We pull the minus out. Square root of minus 1 is what I is. So that so far tells us that the solution is of the type exponential. Remember what we said here. Real part comes here, and the imaginary part is going to be our frequency. Physical meaning of that is the frequency. Exponential of minus 1/2 t, which is like minus TO2, times a cosine of, now we have this peculiar frequency. Be careful that 2 is outside of this radical and t is also outside of that radical. The whole thing in a parenthesis is argument of cosine. You have to understand this thing very well to be able to use either a software or just do arithmetic with it. So b sine of same ingredient. So radical 39 over 2t. Okay, next is imposing the initial conditions. So for that I need the derivative as well. You can learn how to differentiate this thing and make a shortcut for yourself, or just go through the process every time. We're going to do a little bit of time saving in writing it. First, notice that we have a product here. We have to apply the product rule carefully. So our problem is going to be a little bit lengthier than the first type of these second order equations. So derivative of this will be derivative of exponent, which is minus 1/2. Then all of that. So minus 1/2 of this times this entire thing. After you do a few of these things, you create some shortcuts for yourself so that the amount of writing becomes a bit less. But right now, let's write the whole thing. In the product, now I have to differentiate the second one and multiply by the first. So let me start doing that. When you differentiate either sine or cosine by the chain rule, the derivative of these things is going to give you a radical 39 over 2. This one will give it, and so will this one. So I factor both of them and put it outside. So this is a little bit of cleanup process, but if you want to write the derivative any other way, be my guest. So this factor is part of the chain rule applied to these two functions. Then we still have the exponential, that one's sitting on the side. You remember derivative of cosine will be minus sine and derivative of sine will be cosine. So I'll have minus a sine of that expression, and derivative of sine becomes cosine. I will have b cosine of radical 39 over 2t. If you were not comfortable with how I wrote this thing or how I derived it, just go ahead and do it your own way, and then come back and compare against these two. So up to now, pretty much all the steps are things that you are supposed to go through for solving this. Now we are going to impose the initial conditions. So y0. Now let me again hope that you guys keep using that pause button. What is y0 equal to? What is y0? Well, we have the way we get our coefficients is that y0 is given to us as an initial condition, and y0 here also boils down to something in terms of the coefficients. On one hand, it was given as 0. On the other hand, exponential of 0 is 1, cosine of 0 is 1, sine of 0 is 0. So y0 just boils down to a. Okay, so that should give you clues how to make a shortcut for yourself. y0 is just a, and y0 was given to us as 3 originally. So initial position 3 is used here. Next, y prime 0. Can you come up with a quick recipe for what is y prime 0? You just have to go replace time by 0 here and clean it up. First one, we'll have a times minus 1/2, is that right? Minus 1/2 a. Second one is b now starts to play a role. It's a b here times square root of 39 over 2. This is what y prime 0 is. And this is supposed to be 7. Do you see the shortcut? This minus 1/2 is the real part. Radical 39/2 is the imaginary part. It always boils down to that. So we have to figure out what a and b are here. Well, a is already given to us on a silver platter. It's just a is equal to 3. We take it and put it here, and then we get our b. So again, a is just 3, and then b, radical 39 over 2b becomes 7 plus 1/2 a, which is going to be 7 plus 3/2, which is going to be 14, and 3 makes 17/2. So I divide and get my b to be 17 over square root of 39. Again, many students coming from engineering side immediately crank up their calculator and try to convert this. And again, the suggestion is almost always that's a bad idea. It's great for engineering calculation that you're going to do later on, but now we want the so-called exact answer. Now it's not time yet for approximation. We write the exact one, and then we come back. And that's an issue that you're going to be facing when you are solving problem on WebAssign, to know the difference between exact and approximate. The WebAssign doesn't tell you anything about how many decimal places it expects. It means it wants the exact answer. If it tells you, for example, 5 decimal places and such, then you carefully use your calculator. At any rate, we are ready to write our answer. We say y is exponential of minus t over 2. Then a was 3. Cosine of radical 39 over 2t, all in parentheses, and b became 17 over radical 39 times sine of radical 39 over 2t. Okay, here's our solution, y as a function of time. We got the solution, and I hope you go ahead and check your solution versus this. Make sure you got everything right. If there was any issues anywhere, you want to go and see what was your source of your error and correct that. Now, part 2 of the problem. We look at this, say due to this negative exponential, this is going to decay. We have oscillation here, where the sine and cosine gives us an oscillation. This is reducing the amplitude of this oscillation as time goes on. The question is, at what particular time would the amplitude come down below a certain level, and that is typically called either a critical time or a threshold time or something like that. To figure out when that's going to happen, we have 2 avenues ahead of us. One is to use trigonometry, a bit of advanced trigonometry, to simplify this and estimate for ourselves what t is going to be. So that's one approach. And we are going to come back to that style perhaps a little bit later on when I talk about phase shift and the amplitude of response. But for now, let's go ahead and again make use of that very useful software we talked about several times, Desmos, and see how we handle the same question over there. So we are going to go ahead and here's our Desmos. We go ahead and type the function we just got. So exponential of minus t over 2. So I step forward, and then I have 3 cosine of. Now you have to do this thing carefully. It was a square root of 39. Square root, you can just type SQRT, and that's going to give you your square root to you. Or you can use power of 1/2. So 39. Then we step outside by using the right arrow, t, and then divide by 2. And then close the parentheses. It's very important that you notice what went on here. So t is outside of the radical, and this number is outside of the radical, and those things have to be done carefully. Plus, then we have 17 over the square root of 39 again, right arrow, sine of the same thing, sine of SQRT 39. Step to the right, t over 2. That closes the parentheses for sine. We had the parentheses for this oscillatory component. We close that, and that does the job for us. Okay, that is the response of this. You see this huge oscillation, and that is irrelevant to us because we have to look at the whole event after time equal to 0. So it's time equal to 0, and then we have this oscillation. As we said, this is a dying oscillation problem. That is what we talked about essentially from the first day. We said the title of this course could be Vibration Analysis. We talked about what was it? Tuned mass damper. If you viewed that video, that's that one. It was a skyscraper that was oscillating like this, and they wanted to do something about it. At any rate, so we want to know when the oscillation has died down for us. To see that visually, we go ahead, create a threshold for us. That was 0.01, and also minus 0.01. The oscillation might have gone to the positive 0.01 or negative 0.01. We notice that here we cannot see much because these limits are very small. Everything is squished to each other, and we cannot see that. So we have to go adjust our scale. So essentially like putting a magnifying glass on this thing and see what's going on. So I go open this. So on y-axis, I see the oscillation. I want to put a magnifier. So when I put the magnifier here, of course, I'm not going to see this top and bottom anymore. I'm just going to focus around the time axis. So since I want to see the oscillation, let's go, for example, focus on a little bit of magnification between minus 0.1 and 0.1. Let me again point out to you that the blue line is representing the high point, the green line, the bottom point, and this strip is kind of like a trap. You can think about it as a trap. We want to make sure that our oscillation enters the trap and stays in it. So for example, here enters the trap but then exits it. Again, this happens several times because the oscillation is much larger than that. Gradually, we see that the oscillation is getting tamed. Here it enters the trap, but here it exits the trap. This is the last entry into the trap. And after that, forever, it is inside that trap. That is, at this time, the oscillation has become less than 0.01. Notice that we need to watch out both high and low. This was a negative value of the position, but still that's significant. So at what time has this thing happened? So you can click on that point on decimals, and it actually solves the equation for you and tells you that that location is at time 11.518. So it gives you the answer to 3 decimal places. 11.518. Now, if you want more accurate answer there, we have to go through some song and dance to get 4th decimal place or 5th decimal place. But for now, let's say 11.58 is a good answer we have. Is it possible to get the same answer some other way? Well, we have to write that software for ourselves. So there is another course called numerical analysis. I hope that sometime in the future you take that course. How does this software figure out that intersection point? That is subject of another course. You might have seen something related to that in your calculus class under the so-called Newton method for solving an equation. There's still a third way of doing this thing, but for now, I guess we have one answer here. So we have tau turned out to be 11.518. And so what we have is that when t exceeds this, as a result, y for all times after that, if it's positive or negative, so I take an absolute value, the magnitude of that oscillation has fallen below our threshold value of 0.01. So that is, for now, is our favorite way of solving this. And perhaps in a couple of lectures, we come around and talk about estimating that, that value. We wouldn't get exactly 11.58, but we are going to come very close to it by using the concept of resultance, which is a significant issue itself in engineering application. Okay, so what did we do today? Let's go back. We considered homogeneous constant coefficient cases. I listed for you all 7 possibilities with emphasis on what if one of these entries is 0. Make sure not to make a mistake on those cases, so all the bases are covered. And then we took off the kids' gloves and took a look at the problem, a little bit more involved than before. Some physical significance, some numbers not so friendly as before. So our characteristic roots turned out to be these rather weird numbers. And then still we get a solution. We paid attention that this is a dying oscillation. And after we found the A and B, we used the software Desmos to figure out when the oscillation has died down to a specified limit. Okay, you're going to have quite a few homework problems related to this. So it's time to go back to work. And we are going to have more to say about this type of problem coming up in the future sections. Okay, until next time, good luck and God bless.